lesson 3, last day on Tuesday, like I said, we talked about mass by volume, so we'll just pick one here to do. Before we get to that, do not forget mass by volume. 3 important things right here, okay? Remember, if you see percent or PPT or ppm, we need to make sure that we remember that's a mass by volume concentration. What does that mean? Well, for example, let's say you had a 2.15 ppt solution. You have to remember that, of course, 2.15 ppt means 2.15 grams in 1,000 milliliters. Okay? So you'd be looking at that type of question there. Equivalent fractions, yes? So you might want to know, for example, how many grams of solute should I use if I wanted to use 400 milliliters only, for example? Well, once again, of course, you could cross multiply and solve, okay? We need to know how many grams of that. So cross multiply, solve, or this is a factor of 2.5. If you divide by 2.5 there, then you could divide by 2.5 there as well, okay? 1,000 to 400 is 2.5 times smaller, or factor of, so 2.5 times smaller that way as well, okay? Or factor of 2.5, divide by 2.5, okay? So that kind of thing there. Okay, that's what we did on Tuesday, and I gave you a few questions to practice on that. Now, today, we are going to move on to something called molar concentration. I would compare this to your PV equals nRT kind of question in Unit 2 gases. That's what this one does. Okay, same importance kind of thing. Most of the time, we're going to be talking about molar concentration. Remember, I told you guys last day that mass by volume concentration is fine. If you had 12% salt solution, well, 12% salt solution is 12 grams in 100 milliliters. But if you had 12% sugar solution, it would also be 12 grams out of 100. It's not very specific. In other words, salt, so if you had to drink the salt water, well, it tastes pretty gross. If you had to drink the sugar water, it tastes, well, sugary, right? So it's not very specific, that 12%. So what we're going to look at today is being a little bit more specific. And how do we become more specific? We involve what we call the molar mass. We actually talk about that specific compound and use its molar mass. Okay? So right here, the molar concentration of a solution is used to compare the amount, of course, is moles, to the volume that you've dissolved it into. So here we go. N is, and is not moles, and is the amount, which we measure in moles. Okay, so that's what that stands for. Please copy these down. V is going to be the volume in liters. Okay, so this formula, once again, will do liters only. Okay, and C is what we call the molar concentration. Molar concentration, and we measure that in moles per liter. Okay, moles per liter. There is other terms that you will hear besides just molar concentration or moles per liter. You will hear the term sometimes, and especially later on here, I'm going to probably refer to them more as molar solutions. Okay, it's just another term for this, so we don't say molar concentration, we sometimes say molar. Sometimes you will see a big M here, and big M, you think, oh, that must be molar mass, and the answer to that is not necessarily. So the big M refers to basically molarity, as it's called. Okay, molarity. Usually with acids, very common with acids. But you may hear that kind of that term as well. So the big M, you'll know the difference. It'll be a concentration type of question. You'll know the difference when you get there. I just take a little time, a little practice, but you'll know the difference. Okay, but usually we'll use this here, moles per liter. But sometimes you will see that abbreviation with a big M. Okay, so it might be 5.84 molar, for example. Okay, And like I said, usually the big M you'll see on acid containers, things like that, quite often. That's where you'll see it. Okay. So let's take a look at a few examples here. The first ones are pretty straightforward. We're going to start pretty basic, and then we're going to work up from that. And really, they're not going to get overly complicated here. Okay. So calculate the concentration in moles per liter. So when you see that, you know that you probably have to use this formula here today. C equals N over V. Okay. With this formula, by the way, yes, there's a very good chance. Oh, I should have put that on the last page. My bad. Don't forget, there's a very good chance you'll be using that formula there as well. Okay? N equals little m over big M. So we're going to be dissolving a mass, some kind of solid, into some kind of volume. Okay? So we're going to use that as well. But we're also going to include the molar mass, which makes it more specific. You know, salt has a different molar mass than sugar does, for example. All right. So looking at this here, we have calculate the molar concentration. So that's C. That's what we're looking for here. In 1.3 moles and 1375 milliliters of solution. We need to change that into liters. Okay, like so. So 1.375 liters. All right. Dividing these two here. I actually forget the answer here, but it's 1.3 divided by 1.37. Oops. We get 0.945 moles per liter. Okay, is how you would record that. Significant digits, as always. We need to look at 1.3, which is 2, and then 4. So we can only have 2 in our answer here. Remember, the 0 in the front doesn't count. So we'd have to record that, 0.95 moles per liter. Okay? All right, that one's pretty straightforward. They already told me the moles, they told me the volume, and I just had to divide the two in the appropriate units to get that. Okay? Next one here says we have 37.5 grams of solute, and they tell us that solute happens to be magnesium bromide. So magnesium bromide, magnesium is a 2+, bromide is a 1-. It's an ionic compound, so we need to swap, drop, and reduce. Magnesium bromide. Okay. We have 37.5 grams. We're going to put it into 350 milliliters of water. What's the molar concentration? Once again, what's the molar concentration? So I'm looking for C in this case. N, I do not know at this current time. Okay. V, though, I do. It's 350 milliliters of water, so that would be 0.350 liters. Okay. So I can put that in there. N I don't know, but I do know I have 37.5 grams. And I can figure out magnesium bromide, of course, molar mass. So let's see, molar mass 24.31. Oops. And I think bromine is 79.9 times 2. So 184.11 here. Okay, grams per mole. Dividing those two, that'll give me N, 37.5. So 0.2036. And once again, we don't want to round that number, of course, right? We want to keep that unrounded number. We're going to bring that number and we're going to put it in over here, of course. Okay, so now we have moles over liters. Divide the two, and that'll be what we call the molar concentration. So dividing by 0.350, we get 0.58195 moles per liter. We look at significant digits. Okay, 37.5 is 3. 350, 3. Divide. That's what we should have in our answer. Yep. What's that? Sorry. No, because when you put the solute in, usually we're assuming, in most cases, the amount of solid that we put in there is going to dissolve completely. Okay, I mean, if you overfilled it, yes, the solid would take up some space, and you would have more. You would probably increase the volume. You're not really increasing the volume of the water, though. Usually, to make these, which we will make these, you'll measure out the water first, and then you will dump in. You never change the volume of the water. You will dump in the solid afterwards, right? Yes, does the volume maybe perhaps go up a little bit? It may, due to undissolved solid, right? I mean, you might end up with an extra millimeter or something like that kind of thing of water. It's pretty negligible, but usually in most cases we assume that it dissolves. Since it dissolves, it works its way into the in between the molecules, and therefore there's no increase in water size. Okay, like any milliliters or anything like that. And like I said, usually we measure out the water first anyway, and then the solid gets dumped in after. Okay. So 0.582 moles per liter, 3 significant digits because you have 3 in the question. Okay. All right. Now, this one here, of course, as always, you can solve for any one of these variables. So don't forget, not only C equals N over V, but maybe in some cases we want to solve for M or big M. Maybe what's the molar mass of this solution? Okay, what's the molar mass? Which one are we talking about here? Or we might want to solve for V or C, or in some cases you may even want to solve for N. Okay. In this particular one here, it says calculate the volume. So we actually want to look for V here. Well, to solve for V right here, I'd probably do a little cross multiplication. N times 1, yes. And if we're looking for V, I'd probably say N over C, yes. So rearranging the formula, C equals N over V, however you wish to do that, I don't care. That's up to you. If you can rearrange PV equals nRT, you can arrange C equals N over V. Okay? If you can rearrange N equals little m over big M, you can do this one too. Okay? So V, if we're looking for V, we need to know N and C. Well, right now, we actually know one of those two things. We know C. They told me the concentration. How do I know this is a concentration? Because it says calculate the volume of a 1.8 times 10 to the negative 2 moles per liter. That's the concentration. So I know the concentration, 1.8 times 10 to the negative 2 moles per liter. Okay? What I don't know is N. And I'm not actually told what N is in this question. Once again, though, I can figure it out. I have 350 milligrams. So we'll change that to grams, 0.350 grams. Okay? Molar mass. Well, I know it's calcium sulfide. Calcium sulfide looks like this. 2 plus, 2 minus. Swap, drop, and reduce. Yes? Calcium sulfide, 2 plus, 2 minus, etc. So 24.31. And what is it, 32.07? No, calcium, sorry, that's 40.08, isn't it? And 32.07. So that's 72.15. Okay, 1 calcium, 1 sulfur. And we can find N from this, of course, which is 0.350 divided by that, 0.00485 moles. Now we know N. We can take N and put it back in over here, of course. So 0.00485 moles. And we're going to divide those two. Okay, number still in my calculator. When you go to divide this, remember, you have to do the order of operation here. You actually do need brackets for this one. Because if you don't put brackets, you're going to be off by a factor of 100, because you're going to be taking the 0.004 divided by 1.8, and then you're going to times it by -2, which is very different. Okay? So when you do this, make sure you put brackets, especially scientific notation. Okay? So divide by 1.8 times 10 to the -2, which I just didn't use brackets there. That's not good. 1.8 times 10 to 2. And we get 0.2695, and of course that would be in liters because that's what this formula does. Volume is always in liters. Okay. So significant digits wise, let's see. What do we got here? Well, 2 here, 3 there. So I guess we could only have 2 in my answer, right? 2 and 3. So 2. So remember the 0 in the front doesn't count. So the 0.27 would be your 2 significant digits there. Okay? Now, just a few things in note here, and then we're pretty much done. That's it. That's all there is to it. Once again, you could be asked to solve for any one of those variables. Okay? Just remember, of course, that when you're looking at this, right, you can, like I said, you might be asked to solve for the mass. How many grams do I need to use? Well, we'd have to give you this and this. You could find that, which, by the way, would be the same as that. If I told you what we were trying to, calcium sulfate or nitrogen trihydride or some type of acid perhaps, you would know this as well. Check, and you could find that. Okay? But once again, as you know, these two formulas are linked together. You could be asked to solve for any one of those up there. Okay? So just a matter of what information do you have, what are you looking for, how are you going to work that out so you can find that. Okay? So that's the first thing. The second thing, when I talk about this part down here with brackets, 1.8 times 10 to the negative 2, usually molar concentrations are not that big a number. Okay? So that's a very common molar concentration, 1.8 times 10 to the negative 2, 0.018 moles per liter. That's not unheard of. Okay? Can you get more concentrated? Sure you can. But usually when we talk about these concentrations, they're usually smaller numbers because you don't need a lot of sugar especially if it's a small volume. If you have just 100 milliliters, you don't want to put 5 grams of sugar in there, because if you put 5 grams of sugar in there, it might not even all dissolve, right? So we talk about, like, for example, maybe measuring out 0.10 grams of sugar. All right, well, what is 0.10 grams compared to the molar mass of sugar? 0.10 grams, and I think sugar is about 342. So 0.10 grams divided by 342 roughly is 2.92 times 10 to the negative 4 moles. Okay, and if I put that into 100 milliliters divided by 0.1, the concentration is 0.00292 moles per liter. Okay, that would be a typical type of concentration for that. Very, very small concentrations. So you will probably see a lot of times 10 to the negative 2, times 10 to the negative 3 concentrations. Can they be more concentrated? Sure they can. Okay, especially when we get to the acids. What's the original concentration of acid? Depends on what acid we have, but they can be as much as, if you think about this, 17 moles per liter. Okay, which turns out to be a pH of -2, -1. Okay, so you can get very concentrated things, but at the same time, if I ask you to make something, obviously I'm not going to give you 17 molar hydrochloric acid. That's not smart. So we usually dilute them or make them weaker or use them more like this here, okay, where they're less dangerous. All right? All right. So I think that's pretty much that.